Alrighty, this will be an optional one. I just want to, how when I was with you guys, I would occasionally do an absolutely obnoxious example just to sort of distill kind of what we were talking about. The obnoxious examples, while they won't pop up in your tests, are of course useful. This video, as a result, will be, like I said, useful, but isn't absolutely necessary to understanding implicit differentiation. But it is kind of a neat problem, and so I wanted to go over it with those of y'all who actually wanted to watch it. This is the equation right here. X squared plus y squared minus 4x squared is equal to 2x squared plus y squared. Now, this is what is called the limison of Pascal. Okay? There are 4 equations of a tangent line at x is equal to 1. And let me go ahead and show you that. Okay? This is the limison. That is x is equal to 1. And notice that x is equal to 1 hits the limison in 4 different places. Now, if I were to ask you for all 4 of those, there's obviously a little bit of thinking that can go into this that can make our job a little bit easier. Now, you only really have to find 2. The reason you only have to find 2 is because of the symmetry, right? Whatever this equation is right here, the one with the one that goes right along here is going to be the negative slope and have the negative y value that corresponds to it. Okay. So really, let's just concentrate on finding the 2 positive tangent lines. The one that goes here that looks like it meets at 1, maybe 2.55 or something like that. And one that looks like it's at about 1, 1, okay? Now, let's go ahead and, first of all, let's go ahead and find the ordered pairs before we start differentiating anything, okay? Now, if I want to find the ordered pairs that correspond to x is equal to 1, I simply have to plug in x is equal to 1. So I have 1 plus y squared minus 4 squared is equal to 2, 1 plus y squared. And then I just need to solve for y. So this is y squared minus 3 squared, or 2 plus 2y squared. Now that looks a little bit nasty, but you got to remember that this expands predictably because it is a binomial squared, and you know what perfect square trinomials look like. And then when I start gathering things on this side, all of a sudden I have a quasi-quadratic that actually factors very, very easily. I have y squared minus 7 and y squared minus 1, and therefore my ordered pairs are 1 plus or minus root 7 and 1 plus or minus 1. So I have 4 ordered pairs. And of course, root 7 is just a little bit more than 2.5, and we know how to estimate square roots and stuff like that. So, okay, I'm just going to concentrate on the positive ones, though, right? We looked at it, and we basically, our ordered pairs confirm the symmetry that we saw in the graph. Now it's time to go ahead and deal with differentiating this bad boy, okay? Now, this can be a bit of a chore, but you have to remember that you're not looking for the derivative per se. You're looking for the derivative at a particular point. So, we know that we're going to be solving for y prime. We can do a few things to sort of help ourselves out along the way, and I'll show you what I'm talking about. Now, let's go ahead and differentiate that stuff squared. Okay, so 2 stuff times the derivative of stuff, and that's 2x plus 2y, y prime, minus 4. And you're thinking, oh, that's 2 trinomials. Ugh. And you'd be right. Well, let's go ahead and rewrite this as 2x squared and 2y squared. If we distribute that 2, it ends up being a little bit easier. 4x plus 4y, y prime. Now, we can go ahead and divide through by 4, right? There's a 2 here and a common 2 here, and there's obviously a common 4 on this side. So if we divide through by 4, we wind up getting is equal to x plus y, y prime. Now, you're not looking forward to multiplying the trinomial times the trinomial. And what if I told you that you didn't have to? Okay, now remember, all we're looking for is isolating y prime. So why don't I treat this by strategic grouping as a binomial? Okay, and remember, I've told you ever since Algebra 2 that if you don't have to multiply things out, remember it's that constant need that you feel coming out of Algebra 1 that you have to multiply it out. You don't have to multiply it out. I can go ahead and take this and distribute it across here, but when I distribute it across here, there's nothing that says that I actually have to multiply this out. Why would I, right? Okay, and then of course, there's nothing that says that I need to multiply this out. So, why would I, okay? But I have isolated the y prime to this large term right here, and therefore I can go ahead and push that over to the other side. And there's nothing that requires me. And so I'm going to bring the x over here. I'm going to take this large term and push it over here. And in doing so, I'm going to go ahead and I'm going to factor out the y prime. Now, of course, this is going to wind up being subtracted from this y prime term. So, and this is going to make the arithmetic a little bit easier for us, okay? And therefore, I'm going to have x minus 2, x squared plus y squared minus 4x minus x. All of that over, and I can go ahead and pull out the y if I want to. 1 minus x squared minus y squared plus 4x, and all of that is equal to y prime. Now I have the ordered pairs, right? Remember that the ordered pairs were 1 plus or minus 1 and 1 plus or minus root 7, okay? Now, it's good to have this y out right here for when I plug in the root 7, because that y is the only y in here that is not squared. Okay, so basically that cuts down on my arithmetic troubles as well. So let's go ahead and evaluate this at 1, 1. Okay, so that gives me negative 1 when I plug it in for x minus 2. And that gives me 1 plus y squared minus 4, or y squared, or let's go ahead and plug in the 1 for the y as well. So I get 1 plus 1 minus 4 minus 1. All of that over 1, 1 minus 1 minus 1 plus 4. Okay, so I've evaluated the derivative at 1, 1. This is going to be negative 1 times negative 2, which is positive 2. 2 minus 1 is 1. And this is going to be inside the brackets 5 minus 2, or 3. So obviously, that's 1/3. And therefore, the corresponding equation of the tangent line is y minus 1 is equal to 1/3 x minus 1. Okay, well that's easy enough. That means that the 1 for 1, negative 1, has the negative slope and the negative y value. And so, boom, because of symmetry, I've already got 2 of my tangent lines. Now, here's the only difficult part. The only difficult part right here is actually evaluating it at 1 root 7. Okay? Well, let's go ahead and do that. Hold on, let me situate this. Small desk, unfortunately. Okay, so let's go ahead and plug in. I know that when I plug in 1 for x, I'm going to get, remember, I'm still plugging into this right here, okay? 1 minus 2, and then 1 plus 7, because the root 7 is going to get squared here, okay? Minus 4 minus 1, all of that over root 7, 1 minus 1 minus 7 plus 4, okay? Now I'm going to go ahead and clean that up for you. You're just going to have to go ahead and trust me. This is 5 over 3 root 7. And so the equation of the corresponding tangent lines are y minus root 7 is equal to 5 over 3 root 7 x minus 1. and y plus root 7 is equal to negative 5 over 3 root 7 x minus 1. And then I'm done. And it didn't take me a whole lot of time. I just had to, the hard part to remember was the stop, think, then do. Now, most people, just because they haven't gotten over that knee-jerk sort of just that inborn desire, they have to multiply. When they see two polynomials next to each other, an Algebra 1 student sees those next to each other, and just to leave it unmultiplied would just be unthinkable. And I'm telling you, leave it unmultiplied, okay? Don't even think about multiplying those together. Because if you go ahead and leave it in its unmultiplied form, then you wind up getting something that is not all that difficult to plug values in for here, especially if you think ahead and pull out this y because that root 7's coming down the pike. Let's go ahead and look at the graph, okay? The graph is going to be instructive. Now, I've already gone ahead and done this since I wanted to be able to show you. Let's go ahead, boom. Do you see that? And let's turn on that one as well. And let's go ahead and turn all those on so that you see the fact that we did indeed find that particular, we did find it correctly is what I'm saying. Okay, and we can see that, I mean, unfortunately, when you're dealing with grapher, you have to, I haven't found a way around doing SQRT for the square root. But we see that it does have a point of tangency. It does look like it's mimicking the slope of the curve at that point. Now, some of you are looking at that original equation, and you're thinking to yourself, well, if it's a limison, and I know my conversion, then is there a way to do derivatives in polar? And the answer is yes. And those of you that are in BC or continuing on into Calc 2 when you get to college will get to see that. And when we get there in the for you BC guys, I will try to remember, or if I don't remember, please do, that we can come back to this exact problem and redo it in terms of polar, because that actually would, I think, be rather instructive. I hope that that was at least a little bit helpful in terms of distilling what we're trying to do in implicit differentiation, and you know how nasty the problems can get. And that, of course, took us about 10 minutes for me to walk through it. If you were walking through it all on your own and didn't have to sit and ponder, it'd probably take you less time because you wouldn't be having to talk somebody through it. But that's it. I'll go ahead and start working on some videos for the next section in the book, which, if I'm not mistaken, is derivatives of logs and logarithmic differentiation. And it's there that I'll finally get to explain to you why the derivative of e to the x is e to the x. Hope it was helpful, guys.